Welcome to my kitchen. So here I have a glass of water with some blue food dye in it. But just imagine instead of a glass with blue food dye in it, it were like a chemical reactor that had some waste products in it. And I wanted to flush in some fresh reagents or some water to clean it out. So let's say I wanted to take some water to clean out this old chemical reactor. And basically what I did was I turned on the water. And fresh water came in, mixed pretty thoroughly with whatever was left of the old stuff, and then exited the container. So, I have some flow rate in, some flow rate out. Those volumetric flow rates balance, but I'm looking to sort of get rid of all of this old reagent here. So, it overflows. Eventually the old stuff will all be gone. You can see the color's getting lighter, it's getting clearer, it's getting clearer, it's getting clearer. But it's taken a while for all of that blue to go away because, because it takes, it's mixing. There's always a little bit of it, of the old stuff left, and eventually it will take some amount of time before all of the blue stuff, all the old blue stuff is gone. So you can imagine if you were an industrial engineer looking to clean out one of your old reactors, you might be interested in two things. One, I don't want to waste a whole bunch of time washing stuff out if it was clean 20 minutes ago. But also, I want to be sure that I've washed out all of the old stuff so there isn't anything contaminating a new reaction, a new batch for that reactor to process. So I want to balance thoroughness versus expediency. And with fluid mechanics, we can model this process by which the old stuff gets replaced with new stuff, and we can say, hey, how long is it going to take for me to get 90% or 50% or 99.999% of the old stuff gone and replaced with new stuff? So let's model it. Let's do some fluid mechanics. So let's do another example problem with conservation of mass. And we can follow the same example problem strategy we did before, where we organize our problem info into knowns and unknowns. We define a control volume, we break up that control volume sensibly, we work out some integrals on the right hand side, we work out the left hand side, we do some algebra to cancel or solve or organize our results, and then we do some sanity checks at the end. So first, let's organize our problem info and talk about knowns and unknowns. So let's try to mathematically model something, and it could be a tank reactor where we're trying to flush it with some cleaning fluid, or it could be the cup of blue food dye and water that I had in my sink just a moment ago. So let's imagine I have some inlet. Let's frame this in terms of the reactor so it feels a little bit more like bioengineering. So let's say I have some reactor like this. And let's say it's one of these reactors that has these kind of impellers in it that spins around and really mixes all that stuff very well. So let's say I have some fluid entering. And in this set, rather than talking about it in terms of velocities and areas of the inlet, let's just say I prescribed a volumetric flow rate. And let's just call it Q in, right? So in this Q in would, of course, have units of meters cubed per second. And let's say there's the density, the mass density of my fluid coming in, the mass density of the pure water coming in has some density, let's call it rho in. Let's say initially in the tank, there's some fluid of density, we'll call it rho naught. And this is whatever density the fluid had when it was like totally saturated with blue food dye. So this is the initial density when it was sort of fully blue food dye. However, we're looking to, we wanted to know, hey, how long do we have to flush in this new stuff in order for what started as rho naught to like get, most of 99% of the way or 90% of the way or some arbitrary amount of the way towards rho in, right? So, with time, our density in the tank is going to start at rho naught, but eventually it's going to approach rho in. So we want an expression for, let's say, density as a function of time in the tank, right? So whatever density in the tank, we want an expression for sort of what this density is as a function of time. And we're going to assume, because we have this impeller here, that a single density kind of applies to all of this stuff in the tank, right? So this impeller, this mixer is, we're going to assume that basically as soon as fluid gets inside the tank, it's well mixed and homogenized with it's well mixed once it gets in the tank. And I guess the turbulence of all of the stuff entering my cup kind of simulated that process, right? So we have some volumetric flow rate in, some density in. Initially there's some density of stuff in the tank, but we want an expression for how that density transitions from this initial density towards eventually becoming fully replaced with whatever the inlet was. And there we have it. We're going to assume that we know the volume of the tank is a known constant, and we're basically going to assume that the tank starts fully full, full to the brim of fluid, and remains full the entire time. So assume the tank starts full, stays full. So basically, any volume of stuff, any volumetric flow rate in, is going to need to balance for some volumetric flow rate out. Right. So, I guess for the time being, I'll say there's some fluid exiting the tank, and with some density at the outlet as well, and we'll sort out what these are exactly in just a moment. So. This is ultimately what we're going, ultimately what we care about is density as a function of time of stuff in the tank. And we're going to try to do so in terms of all of these known parameters and time, of course. So to be really rigorous, a lot of times I like to build a list of assumptions. As I'm moving through a problem, right? And I like to have this list of assumptions like sort of explicitly, kind of separate, in its own entity, and that helps clarify, if anyone comes up and questions you on your result, you're like, hey, this result is valid based on these assumptions. So let's start tabulating the assumptions that we have for this problem here. So let's assume the fluid is incompressible. And let's assume that it's well mixed. So it's well mixed within the tank. The tank is rigid, and it starts full and stays full. Impermeable walls. And there we have it. And we can basically, I think that's it. That's all we really need to move forward. So I would say now we've organized our problem info. So what is one of the next steps? Well, one of the next steps is we need to define a control volume. So let's define our control volume. I'll do it in purple here. And remember, we have a couple strategies for defining a control volume. One strategy is we want to make parts of our surface of our control volume coincident with places where we have information, right? So we have information about what's going on at the inlet based on the volumetric flow rate and the density at the inlet. So let's put part of our control volume across the inlet, and let's also put part of our control volume across the outlet. And then let's make the rest of our control volume coincident with the walls of the reactor. And if we make the rest of our control volume coincident with the walls of the reactor, we know nothing should be crossing that, right? So we have information about sort of flow rates, velocity, maybe not explicitly velocity, but something related to velocity.
So part of our control volume is going to be here, part of our control volume is going to be here at the outlet, and we have information about what's going on at the walls, right? So this is a sensible way to define our control volume. And the next step is to break it up into 3 parts. So I'm going to call our inlet 1. I'm going to call the walls 2. And I'm going to call the outlet surface 3. So our inlet is 1, our walls are 2, our outlet is 3, and those surfaces make up a complete and fully enclosed control volume. So if we're using the same problem-solving strategy as last time, we organized our problem info into knowns and unknowns. We've defined our control volume, and we've broken up our control volume sensibly. Now let's plop down conservation of mass and start working out some integrals on the right-hand side, and then eventually the left-hand side. So let's put down conservation of mass. So in this case, we have d dt of the integral over the volume of rho dv is equal to minus the integral over the surface of rho v dot n dA. Let's pull the left-hand side. d dt is equal to integral over the volume of rho dv. And we're breaking up this surface into 3 parts. So we'll have minus the integral over surface 1. So what's the density? And we need to be a little careful with density at this point, right? So at surface 1, we're assuming the density is whatever's in the inlet, right? So we haven't yet mixed the inlet fluid with the rest of the tank. We're basically saying, hey, there's it's right at the surface at the inlet. We're still at rho in right here. So at surface 1, density is rho in, and we're given information on the volumetric flow rate. So we're not velocity exactly. So I'm afraid we're going to need to leave ourselves with a v dot n dA for the time being. And we'll square this away in just a moment. So now, integral over surface 2. Well, over surface 2, now we're on the insides of the tank, and we're assuming, density is whatever density we have inside the tank. So I'll just put that as rho. Rho just by itself is sort of signifying this rho as a function of time. But what's v dot n for all the walls of the tank? Well, right at the tank, the fluid molecules immediately adjacent to the wall of the tank can't be moving, right? There's no velocity of the fluid right at the wall of the tank, and in particular, no velocity that crosses the wall of the tank. So in this case, v dot n is 0, so we don't need to worry about any fluid crossing through the walls of the tank. And now, the final surface, surface 3, well, that's going to be rho out. So whatever density of fluid happens to be coming out of the tank is going to be rho. And we have a v dot n that we haven't quite squared away yet, whatever this happens to be for surface 3. Okay, so if we assume, right, we assumed our fluid was incompressible. So that's going to allow us to pull densities incompressible, and we can basically say, well, although density, could be varying with time, across surface 1, we're basically saying it's, incompressible and homogeneous over 1, right? We're saying that, across surface 1, density is all rho in at surface 1, even though at other points in the flow, it's different. Just over surface 1, just over surface 1, all of the density is rho in, right? So we can so over surface 1, density is a constant that we can pull out. And similarly, if it all gets well mixed by the time it gets to the outlet, at the outlet, our fluid density is homogeneous over surface 3 as well, right? So, even though these two densities are different from one another, just across surface 1, it's a constant, so we can pull it over the integral. And just across surface 3, it's a different constant that we could pull out of the integral as well. And of course, we can get rid of this second integral because we didn't have any velocity crossing that surface. All right, so what does that leave us with? Well, that leaves us with the left-hand side, which we haven't fully squared away yet. But we could pull those densities. And if I think about it, what is this density at the outlet? Well, if the stuff came in and got well mixed, whatever density is leaving has to be the same as whatever density is in the tank. So these need to be equal if the fluid is indeed well mixed, right? So some stuff comes in, it thoroughly mixes. Whatever fluid is exiting the tank is essentially a perfect sampling of the well mixed fluid that's in here. So actually this rho at the outlet is this rho that we're ultimately looking for as a function of time. So we're already making some progress towards our desired result. So we now have rho, an integral over surface 3 of whatever v dot n dA happens to be at surface 3. All right, so we're making some progress. We're not all the way there yet, but let's now square away what some of these integrals are. So if I think about these terms, all of these terms in the conservation of mass equation, all of them together, right? This whole term right here, this whole term right here on the left-hand side, all these terms have to have units of kilograms per second. Right? All these terms have to have units of mass flow rate in order for it to be a rate balance like conservation laws tend to be. So if this is a mass flow rate, and mass flow rate has essentially two contributions. One is density, and the other is sort of everything else that's left here. If I think about the density part of it, that's going to be kilograms per cubic meter. So I pose to you, as a pose and ponder, what are the units? What are the units? What must be the units of this last term right here? So pause, ponder, work it out. What are the units of this integral v dot n dA? Well, if you worked it out, it's got to have units of, if this has kilograms per, if together they have kilograms per second, and this is kilograms per meter cubed, it's got to have units of meters cubed per second. What is something that has units of meters cubed per second? Physically, what is meters cubed per second? Well, physically, meters cubed per second is a volumetric flow rate. So these integrals of v dot n dA, these have to basically be flow rates or something very closely related to it. So let's square that away now. What are these v dot n dA right here? So let's work it out. So a v dot n dA, if n is pointing, so let's kind of think about surface 1 right here. So if n is pointing out, and let's say we know velocities, for surface 1, if velocities are, let's say, going in, something like this, then v dot n is going to be negative, right? So what does this mean? So if I think about the integral over surface 1 of v dot n dA, this whole thing has to essentially be a volumetric flow rate, But in the case of like surface 1, if flow is going in, then v dot n, this integral over surface 1 v dot n is got to be a volumetric flow rate. So in this case, this integral v dot n dA over surface 1, this is going to be equal to, in magnitude, it's going to be equal to q in. But because v and n are in opposite directions, we're going to have that minus sign out there. Conversely, and similarly, if we think about surface 3, where the outward pointing normal points in the same direction as whatever velocity, whatever velocity we have at our outlet. In this case, v dot n is positive. That implies that over surface 3, the integral of v dot n dA is going to be equal to essentially to positive q out, whatever this volumetric flow rate happens to be, because v and n are in the same direction. This dot product is going to be giving us a positive quantity. So what does this mean? Basically, we never need to work out what these integrals are, right? Who likes to do calculus but never actually have to do out the integrals? Me, I like to do that, right? We don't actually need to do what these integrals are. We know that such an integral exists, but we can just cut to the chase and put it in terms of volumetric flow rates if those are, for example, given to us as part of our problem statement. So we never actually need to do these integrals out. We just need to think a little carefully about v dot n for what sign goes out front, and then just cut to the chase and put the volumetric flow rates right there, by knowing that this part of the mass flow rate is the volumetric flow rate, which when multiplied by the density gives mass flow rate. So what does that mean? We don't need to do out these integrals. We can just put them straight in terms of volumetric flow rates to get some progress on these results here. So let's put those in. So our left-hand side is still unchanged. So we have an integral over the volume, rho dv. We haven't bothered to make any progress on the left-hand side yet. We now have, so we still have this minus rho in, and we were able to replace this entire integral over 1 with the integral over surface 1 with a minus q in right here. And now for the second term, we have minus rho, right, which we said is rho out, but rho out, since it's well mixed, is just whatever density happens to be in the tank. And then this integral over surface 3, is going to be q out. All right, so we've made a lot of progress here. This is great. Now, let's make even a little more progress towards this. If I have this tank, and the fluid inside, could be variable density, but is incompressible, then whatever volumetric flow rate I go in has to be the same as the volumetric flow rate going out, right? So if I think about Q in, it's got to be the same as Q out, right? However many milliliters I pump in, unless there's like a secret black hole, or unless I'm really compressing that fluid to actually compress it, whatever volumetric flow rate I go in has to be the same as this volumetric flow rate that comes out. So this right here has to be equal to Q in. That's awesome. So how's that going to help us? Well, now we've made a lot of progress replacing with unknowns in terms of knowns. So at this point, we've worked out integrals on the right-hand side. Now the next step is to work out integrals, or is to work out whatever's going on in the left-hand side. So let's work out the left-hand side. And it's often good to sort of start inside and kind of be moving our way out. So d dt integral over the volume of rho dV? Well, let's think about rho. So what rho are we talking about in the tank? Well, strictly speaking, density could vary over the tank. Density can vary spatially in general, so we need to be a little bit worried about rhos that we deal with here. But if we're saying we're well mixed in the tank, there's sort of this one density rho that we're kind of applying to the whole tank and saying that it's well mixed. So in this case, we can replace this sort of as you get determined rho with the rho that we're looking for to kind of solve for as a function of time. So we've put in rho dV here. And now on the right hand side, I can basically say that's equal to Q in times rho in, sorry, not this, rho in minus rho. So already we're definitely making progress here. Now, I'll pause and ponder. Pause and ponder. Can we take this rho all the way out here? Can we take this rho all the way out of the integral, out of the derivative? Can we take this rho and put it all the way out here? So take a moment now, pause, consider. Can we pull this all the way out? The answer is not all the way out, but kind of. So let's look at it a little more deeply. So spoiler alert, we can't pull it all the way out, but we can pull it some of the way out. It turns out we can pull it out of the integral, but not out of the derivative. So what's the key thing? This rho here, because we're well mixed, if we're well mixed, we can pull out of spatial integral, but this density is going to be a function of time, right? Or I guess I should use my red here, right? This density is a function of time, and if this density is a function of time, can we pull it out of a time derivative? Nope, we can't pull it out of derivative, right? So it's well mixed, so we can pull it out of the spatial integral just fine. So it's well mixed. If it's well mixed, we can pull it out of the integral, but we can't pull it out of the derivative because it's a time varying quantity, right? So what does that leave us with? Well, that leaves us with dt of rho times an integral over the volume of just dv left in the integral, and that's going to be equal to q in times rho in minus rho. All right, so let's see if we can make much more progress here. All right, so let's make a little more progress here. Take a moment now and pause and ponder. What is this? Can we make some simplification to this integral dv over the whole control volume? So pause and ponder, what's this? Well, perhaps you've paused and pondered. If you have an integral dv and kind of nothing else inside the integral, an integral dv is just v, and if we're integrating over the whole volume, this integral dv is simply just the volume of the tank, which we said was some known constant, right? If we're integrating over the whole control volume, just dv, then we get v, which is the volume of the tank. So what's this? Well, we can make one more simplification. This is just this quantity in purple here is v tank, and we basically said, hey, this volume of the tank is, we said the tank starts full and stays full. the tank isn't flexing or expanding in any way. This volume of the tank is a constant with respect to time, so this whole chunk can basically pull out of the integral here. So what are we left with? We're left with v tank. And then in that case, the only thing left in this time derivative is rho. So we basically have volume of the tank times d rho dt, which is going to be equal to q in times rho in minus rho. All right, now we have some result, and our goal was to figure out what rho is as a function of time, but unfortunately we couldn't get there with just algebra alone. We have on our hands an equation. It's a differential equation, but it's a differential equation that we're going to be able to solve. So we have on our hands a differential equation that we're going to need to solve. So our strategy is going to be to solve this differential equation, and we might end up solving this differential equation and then needing to apply boundary conditions or initial conditions or something to help deal with unknowns or constants of integration that arise, that come up in the process. So stay tuned. Next steps are to solve this differential equation. So what do we have on our hands? We have a differential equation. The elements in blue, those variables are constants. Rho is going to be our dependent variable, and t is our independent variable. When you look at this kind of equation, it's a first order linear differential equation, non-homogeneous. And we can solve it. Well, we can solve it on Wolfram alpha, of course, if you wanted to, but we can practice our calculus, practice our differential equation skills, so we can solve this via separation of variables and integration. So let's do that. We can try to bring all the terms with rho over to one side, all the other terms over to the other side, and dt over to the other side, and then we'll integrate both sides with respect to their respective variables. So let's go ahead and try to do that. All right, so what can we do? I'm actually going to reverse the order of these two and factor out a -1. And then I'm going to divide both sides by v tank. I'm also going to divide both sides by the flipped version of this. So I'll end up with minus q in over v tank on the right hand side, and I'm going to bring dt over to the right hand side as well. And then we're going to have d rho on the left hand side, and it's going to be d rho over, now remember I flipped these and factored out the negative sign, so now it's going to be d rho over rho minus rho in. So what's our plan now? We're going to integrate both sides of these equations, and we're going to leave them as indefinite integrals now. So we're going to integrate both sides, leaving them as indefinite integrals. Well, if we integrate the right-hand side, what do we get? Well, with respect to time, both of these elements are just constants, right? So the right-hand side ends up being pretty straightforward in terms of integration. We just get minus q in over v tank times t. And what do we get on the left-hand side? If I just covered up this rho in here, you had d rho over rho, what would you get? So let me just imagine this now. Pause and ponder. What would I get if I covered up the minus rho in? What would you get? So pause and ponder. What is the integral of d rho over rho? Well, if you dust off your high school calculus notes, equivalently we could say this is an integral of 1 over rho d rho, or you could just say 1 over x dx, right? You could put whatever variable you wanted here. And if you remember, integral of 1 over x is natural log of x, or integral in this case of 1 over rho d rho is going to be natural log of rho. But we have this minus rho in. So strictly speaking, if we wanted to be totally rigorous, we could do a u substitution, we could get all that stuff. But since there are no constants out here in front of this row, why don't you just take my word for it that on the left-hand side we end up with natural log of rho minus rho in. And I'll give you another pause and ponder, separate from this first one. Pause and ponder. Are we okay? Do we do everything? Have we done, have we got to our appropriate result? So pause and ponder. Are we all right? Well, we're actually not okay. If you've completed your pause and ponder, we're actually not okay because remember, these are indefinite integrals, and when you do indefinite integrals, you end up with a plus c. So we got to put that in here, and I'll just put it on the right-hand side. I could put it on either side. It's arbitrary, right? So we got to have a plus c, and I'm going to put this c in red because it's some variable that's as of yet unknown. We haven't fully squared away what this plus c is going to be. So here we have it. This is our result. And as soon as we square away this plus c, we'll be able to do some algebra to get rho as a function of a whole bunch of known constants and time. So how do we deal with this plus c? Let's deal with it right now. So in general, when you integrate, with respect to time, you generally resolve the plus c business with what's called initial conditions. With an initial condition, i.e. some information about what is happening in your system what's the state of our system at time equals 0. And this is what's going to be useful in this problem. Just as an aside, we're later, when we solve other problems, we're going to do integrations with respect to spatial variables. And generally when you integrate with respect to x, y, z, etc., something like that, and it's an indefinite integral, you resolve the plus c business you get with what's called a boundary condition. Which describes something about your system. So what is our system state at some known x, y, and z value? So something like that. So in this case, in the case of this problem, we're integrating with respect to time. So we're going to resolve our plus c with information that happens at time equals 0. Well, what is the information that happens at time equals 0? Well, if we go all the way back to our problem statement, we know that initially, the density of the contents of our thing was some density rho naught. We said, hey, yeah, our system's going to start with a density of rho naught, eventually progress towards a density of rho in once all of this stuff has displaced all of the old stuff. So we'll be able to get this result here, or this rho naught will inform the development of our final result for density as a function of time. So that's going to help us out. So what is this initial condition? So in this case, at time is equal to 0, rho is equal to rho naught, this known value, this known density rho naught. So the process is then we take this boundary condition, or I guess in this case it's an initial condition, and we sub the particular values of t and the particular values of rho into this equation to help us resolve this as of yet unknown constant. But I'm going to put this on hold and do a little bit of algebra on this before trying to get to this result. So hang tight. So we're going to put on hold and we're going to manipulate the equation first. So what do I mean? I'm just going to do some algebra to try to like unbury rho first and get some of that, right? So if I have natural log on one side, I can take e to both sides to essentially cancel out that natural log. So what does that look like if I do e to both sides? Then I get rho minus rho in is equal to e to the whole right-hand side. So it's going to be e to the minus q in over v tank times t plus c Now, if you remember your rules, if you have e to a sum of two things, that's equivalent to e to the first thing times e to the second thing, right? A sum in the exponents is equivalent to a product, right? If I had x to the fourth, that would be equivalent to x squared times x squared, where 2 plus 2 is equal to 4, right? So if I have e to this one thing plus another thing, that is equivalent to e to the first thing times e to the second thing. Now, c was an arbitrary constant, right? C was, some arbitrary constant. So if c is an arbitrary constant, e to the c, this is also an arbitrary constant. This e to the c is an arbitrary constant. And it turns out, well, it'll make our algebra a little bit easier later on when we're applying our initial condition. If instead of having e to the c and trying to solve for what c is, if we just say, hey, this whole thing is some different arbitrary constant. Let's just call it c star, right? So let's just call this whole thing c star. So we can instead say c star, this expression right here is equal to c star times e to the minus qn over v tank times t. Right, where our arbitrary constant is now this c star up front. So we now have an expression for density. I mean, I guess we could bring rho into the other side if we wanted to, but whatever. Is equal to this. So now let's apply this initial condition to this expression right here. So we can say, hey, at time equals 0, rho is equal to rho naught. So what's that going to be? Well, we now have rho naught minus rho in is equal to c star times, well, e to the minus qn over v tank times t. We're evaluating this expression at t equals 0. So e to the, well, if t is 0, the whole e to this whole thing is 0. And remember, e to the 0 is, well, I suppose this could be a pause and ponder question, but e to the 0 is 1. Basically anything to the 0 is 1. So in this case, C star is equal to rho naught minus rho in. And now you can see why I sort of did this whole C star business. It's pretty straightforward to get what C star is, but if I had to, unvary e to the c, that's a mess, right? So C star is equal to rho naught minus rho in. So now what can I do? I can take this result for C star and plug this in, and now I can have an expression for rho in terms of entirely known constants. So let's go ahead and do that. All right, so when I plug it in, if I plug it in and solve for rho, I get rho is equal to, and I'm just going to bring rho in over to the other side. So I get rho is equal to rho naught minus rho in. This is from the C star times e to the minus q in over v tank times t. And then this whole thing plus the rho in that I brought over from the right hand side. So rho in. All right, great, we did it. So we now have our expression for rho entirely in terms of known constants, and I could evaluate this whole expression at any particular t, any arbitrary t that I chose, right? That's why I'm kind of treating t as a known constant. So what does this mean? This means that I could basically say, hey, you could tell me any time, and I could tell you as a function of all these known constants essentially what the density of the material in the tank is. One sort of manipulation of this expression that I like to do is to sort of rearrange things just a little bit, almost backwards to a form that we had earlier, and I like to form it as rho minus rho in over rho naught minus rho in. And that's equal to e to the minus q in over v tank times t. And you can kind of imagine this as almost like essentially the difference between a difference in density from what its steady state density is going to be divided by what that initial was. You can almost imagine this as like a fraction of some change in density is exponentially decaying, right? So if we think about it, right, this is like exponential decay. Right, so, and exponential decay is going to show up like all over the place in heat transfer and fluid mechanics. It's going to this is not the only time that exponential decay is going to show up in this class, right? So density is basically changing in a somewhat exponential way, where the most rapid stuff, with exponential decay, the most rapid stuff happens at the beginning, and then it slowly asymptotes towards some steady state value. So let's actually kind of work out graphically what that's going to look like. So let's go back to this expression, and we're gonna talk about things graphically. So if I want to think about things graphically, I'm going to create two axes. On the x-axis, I'm going to put my independent variable, t in this case. So as a function of time, I'm going to put on the y-axis density. So this is the density of all the stuff in the tank. And if I want to think about it, pause and ponder. What is the first point on this graph going to look like? So pause and ponder. Where do I place this first point on the graph? Well, hopefully you've done so. Pause and ponder. We can basically put this first point, we can evaluate this expression at time equals 0, right? And at time equals 0, this becomes 1. So I get rho naught minus rho in plus rho in. And this was actually a nice sanity check that I get rho naught back at when I evaluate it at t equals 0. So I'm just going to put rho naught at some kind of arbitrary point on this plot. So let's just say rho naught is right here. Now, I could sort of plug and chug a whole bunch of points out, but I like to when I sort of graph things, I like to think about what happens at t equals 0, and then a lot of times I also like to think about what happens as time approaches infinity. What is the sort of, immediate, and also what is the long-term behavior of this system. So another pause and ponder question. So I guess the first pause and ponder question was what happens at t equals 0. The second pause and ponder question is what happens as t approaches infinity. So take a look at this expression, see what happens as t approaches infinity, and see what we get algebraically anyway. Well, perhaps you've paused and pondered. If I think about what happens as t approaches infinity, I get essentially e to the negative infinity. And e to the negative infinity, is essentially 1 over e to the some large number, which basically means that this whole term approaches 0. And if this term approaches 0, basically this whole chunk approaches 0. And if this whole chunk approaches 0, then I'm left with just rho approaching rho in. And that's physically consistent with what we were talking about right here, right? As time goes to infinity, eventually whatever I'm putting into the vessel is going to displace all of whatever was there, right? All of the fresh water that I put into that cup eventually displaced the slightly blue-dyed water. So as time approaches infinity, let's just say rho infinity is rho in is some different value. There's going to be some asymptote, and the curve is going to kind of exponentially approach this. So as time approaches infinity, we get this exponential approach, this asymptotic behavior towards the input. And this is actually true, this result is actually true no matter what rho naught I have. If I had a different rho naught, let's say some rho naught up here, then the exponential approach would look like this. Basically, if we had some different rho naught, let's say rho naught number 2, it approaches it from the top. If my rho initial density is higher, it still exponentially approaches rho in. If it's lower, it still exponentially approaches rho in. Basically, this mathematical result doesn't rely on one of these being higher or lower than the other. You still get this exponential approach. Finally, I'd like to talk about what happens if I tweak some of these variables, right? So we talked a little bit about what happens if I change rho naught. You can see what would happen if I changed rho in. If I changed rho in, then I'm just essentially changing the level that this curve is going to asymptote to. But what happens if I try to change either one of these, Q in or V tank? Well, let's imagine I take Q in. Let's do this in a different color so we can see what happens, right? What happens if I took Q in and increased it? Well, if I took Q in and increased it, then that's essentially multiplying this contents of this exponential by some larger number, right? So in a sense, if Q in is bigger, then that's kind of making everything essentially appear to happen faster, right? I'm multiplying time by a larger number. So that's kind of making time sort of happen faster. And physically that makes sense, right? If time is happening faster, then I'm flushing new stuff in and flushing the old stuff out a lot faster. So if I'm flushing new stuff in and flushing old stuff out faster, then it doesn't change what level I asymptote to, but it does change how quickly I get there. So if Q in increases, then it doesn't change where I start, it doesn't change where I end, but it does enable me to get there faster. Right? So increasing Q in essentially pushes these curves such that they happen faster. Doesn't change the asymptote, doesn't change the start point, but it does change the rate that I get there. Alternatively, if I took V tank, let's say I took V tank, if I took V tank and increased it, what effect would that have on the curve? So pause and ponder. Add to this sketch here a sketch of what this curve would look like. Let's say I had this rho naught and this rho in. What would happen if I increase the volume of my tank? Well, perhaps you've paused and pondered. If I increase the volume of the tank, that essentially does the precise opposite of what happens if I change Q in, right? If I increase the volume of the tank, then I'm dividing time by a bigger number. So that means time, I'm essentially slowing down time. I'm scaling time by a smaller factor. So it takes more time in order for the exponential thing to happen to the same amount. So if I increase the volume of my tank, then I slow this whole process down, eventually I still start at the same thing. Eventually I asymptote to the same thing. It just takes longer for me to get there. And it's still an exponential shape. So this is basically what happens if I increase the volume of the tank. All right, so what did we did? We did a bunch of algebra to cancel and solve and organize. We did checks. I would say we've already done this check where we made, we talked about what happens if some parameters go up and down, but we still haven't done this check for units yet. So let's do that. So I'm just gonna look at my final result here, and we'll talk about units. Density should have units of kilograms per cubic meter, and we want to see if this is equal to what I get on the right hand side. Well, the two terms that I sum on the right hand side should both have units of kilograms per meter cubed, right? So rho in, that's kilograms per meter cubed already. So these two make sense with respect to one another. What about this junk right here? Well, rho naught minus rho in, this is kilograms per meter cubed. So hopefully the contents here, this junk right here is dimensionless. So I have E to something. What are the units of Q in? Well, that's the volumetric flow rate, right? So that's going to have meters cubed per second. I multiply that by time, which has units of seconds, and then divide that by the volume of tank, which has meters cubed. So all of this cancels out, and it's a good rule of thumb that even the units on both sides of the equation should work out. But anytime you have the contents of e to the something or sine of something or some sort of trigonometric or transcendental function like this, the contents should also be unitless. So not only should the units balance out on both sides of the equation, but the contents of e to the whatever should also be unitless. And that happens to be the case here. So our units check out. So hopefully this result is satisfying. Hopefully now you have the tools to proceed with analyzing transient problems. And this allows us to say, hey, how long is it going to take, right? You could imagine, if we wanted to achieve a particular density, I could do some algebra to solve this the other way and say, how long is it going to take in order for me to wash this tank, to get 99% of the way from my initial value to my asymptote. So it's going to take an infinite amount of time for me to get all the way there, but how can I get arbitrarily close? And we can use this result to solve for that time. So chemical engineers use this all the time in their chemical processing. Bioengineers use this all the time, and hopefully this was worth your time. So good luck with your studying of fluids. Thank you very much for watching. Cheers.